Okay, power series today. This is it, last new lesson of the chapter, right? Yep. Whoop, whoop. All right, here we go. It's a doozy. Warning you right now. Power series. So, disclaimer, don't get bogged down by notation. It's just series. I know it looks scary and stuff, but it will be okay. So a polynomial is a relatively simple function to calculate. They are used in a power series to evaluate a sometimes more complicated function. And actually what it turns out, just so you know, your calculators only know addition and subtraction, multiplication and division, even though they do logs and cosine and sine and powers and all of that. What it turns out what they do is they change it to a power series. Your calculator has the power series programmed in, and that's actually all they're computing. So, all right, so what is a power series? It's just the sum of a sequence with increasing powers of x. Here's an example of a power series where you've got a naught and then a1x plus a2x squared plus a3. So don't get scared. These are just numbers, right? A naught is a number, so you could start with a constant, and then a1 is the coefficient on x, and a2 is the coefficient on x squared, a3 is the coefficient on x cubed, and it keeps on going. Sigma, it's going to start with k equals 0, so then that way we can have a constant term right there. So the a to the k and then times x to the k. This is a power series. Notice k starts with 0, so that way we can have it says general term. I think we meant constant term right there. And then also notice that the coefficients are not necessarily the same. A naught is different from A1, is different from A2. Like they could be the same, but they also could be different. There's no restriction on that. If they are all the same, then that means we have an infinite geometric series. If A is the same on all of these guys, you would just have A times x to the k. We've got A plus A times x plus A times x squared and all of that. So it's geometric if all of the coefficients are the same. But for a power series, they don't have to. You can have different coefficients. What we're interested in is for what values does this series converge? This is so calculus. We're totally, we're not doing calculus, but we're going to use all of this lesson's information next year in calculus. So for what values of x does the series 2x to the power of k converge? So I wrote out a few terms, right? Starting with plugging a 0 into k, you would have 2 times x to the 0, so that's just 2. And then plugging in a 1 into k would give you 2x. Remember the sigma says put a plus sign in between. Plus sign 2x squared plus 2x cubed. So do you see that this is a geometric series? Yeah? You got where your first term is 2, and then what's your common ratio? First term is 2. What did I multiply 2 by to get to 2x? X. Your r is x. And it's geometric, so that means that this guy will converge. Remember we did this yesterday when the absolute value of r is less than 1. But your r is x, so that means it converges when absolute value of x is less than 1. Do you remember how to remove absolute value symbols? This means that it's between -1 and +1. These are the values where the series converges, when x is between -1 and +1.
Sorry, I missed that. Could you say it again, please?
No.
Okay.
Sorry. And it will converge to, the sum is the first term divided by 1 minus common ratio. Yeah, first term was 2, common ratio was x, so that's what it'll converge to. For any constant a, the infinite geometric series, this guy will converge to first term, which would have just been a over 1 minus x for all x when that common ratio is less than 1, so when the absolute value of x is less than 1, and then it will diverge anytime that the absolute value of x is greater than or equal to 1. And then this whole, we found absolute value of x was less than 1, and then we rewrote it. Removing the absolute value symbols means that x is between -1 and +1. This guy right here is what we call the interval of convergence. Any values in that interval are going to converge, right? So any number between -1 and +1, not including them, right? We say it converges, or that's the interval of convergence. Let's find a power series that converges to 5 over 1 minus 1/2 x. And then for what values of x will it converge? All right, so it's saying it converges to. So that means this is the sum of the infinite series, right? So that means your 5 is your first term, and 1 minus r is 1/2 x. Yeah. So I'm going to write it, right? Right, your first term is 5. Your next term would be 5 times 1/2 x. Second term would be, third term would be times 1/2 x. Times 1/2 x to get to the next guy, right? So your terms are 5 plus 5 times 1/2 x plus 5 times 1/2 x times another 1/2 x, so you get it squared on the 1/2 x, plus 5 times 1/2 x squared times another 1/2 x, you get that cubed, plus dot, dot, dot. Do you remember that a geometric series is written as first term times the common ratio raised to the nth power, usually we say, but I'm going to put k here because I used k as an index there. And it's going from 0 to infinity. So that's your general term. So that's your power series. That was that part. Find a power series that converges to this. You find your first term, you got your common ratio, boom, 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 done. For what values of x will the series converge? Well, we know that it converges when the absolute value of r is less than 1, and your r is 1/2 x, so it converges when absolute value of 1/2 x is less than 1. Don't leave it like this, though, right? We want to remove the absolute value symbol, and you do that by putting it between the negative of this guy and the positive. And then you want to solve for x, and we have 1/2 times x here. So if you multiply it by 2, you'd get x. And you can do that as long as you multiply the -1 by 2 and also the +1 by 2. So I'm multiplying all 3 parts of this inequality by 2. And I get -2 from x between -2 and +2. That's your interval of convergence, or the values of the series that will converge. Let's find the interval of convergence for 1 plus x plus 2 plus x plus 2 quantity squared plus x plus 2 quantity cubed. So definitely an infinite series, right? All you got to do is figure out what your r is. So your first term is 1. You notice that your common ratio is, you're just multiplying by x plus 2, right? So this converges when the absolute value of r is less than 1. So absolute value of x plus 2 is less than 1. Remove the absolute value symbols by putting them between -1 and +1. And then you want to solve for x. In order to do that, you need to subtract this 2. And you can do that as long as you do it to all 3 parts of this inequality. So -1 minus 2 will give you -3. 1 minus 2 will give you -1. Your interval of convergence is between -3 and -1. Yeah. All right. So the examples so far were rational functions being represented by a power series. We can also represent other functions. 3 familiar functions, e to the x, sine of x, and cosine of x, all have power series that converge for all values of x. Their interval of convergence is all real numbers. So for now, we're just going to use them. You don't need to memorize them. Next year, you'll actually learn how they're obtained, and you'll actually memorize them and everything. They are obtained using the derivatives and the rule for power series, and so both of these are concepts in calculus, so you'll learn the reasons behind it next year. For now, okay, I'm going to warn you, it's going to look scary. It's really not that scary, promise. It just looks scary. What I'm going to do is I'm going to turn e to the x into a power series, right? Remember how I said to you, your calculator, even graphing calculators, all they know how to do is add, subtract, multiply, and divide. So they take e to the x and it has the power series programmed into the calculator, and this is what it figures out. So here we go. E to the x. The power series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. The pattern is x to the k over k factorial. Writing that in series notation, it's sigma starting with k equals 0 of x to the power of k divided by k factorial. So your graphing calculator has this programmed in, and that's what, when you put in e to the power of 10, it plugs a 10 into each of these x's and multiplies and divides. Crazy, right? All right. Warning you again, it's going to look scary. It's not bad. Do you remember sine of x is an odd function? Do you remember that? That sine of negative x is equal to negative sine of x, and we said it was an odd function? This is going to help you remember. Not that you have to memorize these yet, but next year you will. Sine of x. The power series for sine of x. When you put sine of 30 degrees in your calculator, it doesn't know, it didn't have it memorized that it's, 1/2. It plugs in 30 degrees into each of these x's and computes this polynomial. Crazy, right? Okay. All right, so sine of x is x. This is like you could think of it as to the power of 1 over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Do you see the pattern? First of all, it's alternating in sign, positive, negative. That's where this negative 1 to the kth power comes in. That gives you the alternating sign. We talked about that in an earlier lesson. Did you notice that all of the powers on x are all odd numbers? Odd numbers. Sine's an odd function. Nice. All right, so how do you write an odd number? 2k plus 1 is one way to write an odd number. That's how we're going to do it on here. And then notice that you're dividing by all of the odd numbers factorial. And so in sigma notation, you got the alternating part and then x to the odd powers divided by the odd power, or the odd numbers factorial. All right, I'm going to give you cosine also. Again, you don't have to memorize these. We're going to give them to you. You just need to know how to apply them. But just helping you give the explanation of why. Cosine, do you remember it was an even function? Cosine of negative x was equal to positive cosine of positive x. We called it an even function. Well, these powers match up too. Cosine of x. When you put in your calculator cosine of 3 pi over 4, it puts 3 pi over 4 into all of these x's, and it just adds and multiplies and subtracts. Crazy. Okay, look. Here's the power series for cosine of x. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial. The pattern is it alternates in sign again, positive, negative, positive, negative. That's where the negative 1 to the kth power comes in. Do you see all these even exponents? Even. They're only the even ones. You write an even number by 2 times k. How did I get a 1 though? Because we're starting with a 0. Yeah, starting with k equals 0. So when you, x to the 0 would just be a 1. And then I don't know if you remember this, but 0 factorial is defined as 1. So it matches in the denominator also for this. It would just be 1 over 1. All right, but we got all the even numbers here too, because cosine's an even function, right? And so there you go. All right, again, don't have to memorize it, just need to know how to apply it. So let's do that now. We're going to use the first 7 terms of e to the x to evaluate e squared. So here's the e to the x pattern. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and it keeps on going. We want the first 7 terms, 1, 2, 3, I gave you 4 of them, to do e squared. All right, so e squared means you are plugging a 2 into each of these x's. And we need to go all the way up to what? 1, 2, 3, 4. So to give you 7 terms, I need to go up to x to the 6th. So e squared will be a 1, plugging a 2 into x. You see how it's e squared, so the 2 is replacing the x. So 2 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial. The next one would be 2 to the 4th over 4 factorial plus 2 to the 5th over 5 factorial plus 2 to the 6th over 6 factorial. And that's 7 terms, right? 1, 2, 3, 4, 5, 6, 7. Put that in your calculator and you will end up with 7.3556. Pretty good, huh? Now, if you were to actually put e squared in your calculator, so not all of these guys, you're going to get a different value. You're going to get 7.3891 if I were, rounding to 4 decimal places. So you see, it's pretty close, right? We're off by what? 0.04, right? Ish, something like that. And that was only 7 terms. Your calculator does it to infinity. So if we added more terms, we would have been even more accurate. So this is an approximation, I guess is what we could say. It's definitely an approximation if we're only using 7 terms. Okay. If we were to let the numbers in the series for e to the x be pure imaginary numbers, plugging in an ix in here. I'm not going to show you the proof of it. It's actually a very simple proof, but you'll actually end up getting, when you plug in an I to the x and then simplify all the i's using the powers of i's, and then grouping up terms, you'll actually end up getting that e to the ix is equivalent to cosine of x plus I times sine of x using those power series. And then since, if you remember from, I don't remember what chapter it was, but it was the complex numbers and in polar form and stuff. Since any complex number can be written in polar form as r times cosine of x plus I times sine of x, we can now say any complex number can be expressed as r times, since cosine of x plus I times sine of x is e times ix, or e to the power of ix, then this is equivalent to r times e to the power of ix. Isn't that nice? So let's express this complex number in the form r times e to the ix. All right, so what we need is r, and then x is the argument or the angle, right? And we'll do it in radians. All right, so how do you find r? Do you remember that was called the modulus? Or it's Pythagorean theorem. It's the distance from the origin out to that point, right? It's the square root of 3 squared, if I can talk, plus the number in front of I is a 1, so plus 1 squared. You're just doing square root of a squared plus b squared, which ends up giving you 2. So the modulus is 2, or that's your r. Yeah. Now we need to find the angle, which your book calls the argument. Well, here's what I know. I know that cosine would be rad 3 over 2, and sine would be 1/2. Your angle is pi over 30 degrees, or pi over 6. And so I'm going to plug that theta is your x value there. And so in polar form, I'm going to write it in the regular polar form that you learned before first. R cis theta, right? So r times cosine of pi over 6 plus I times sine of pi over 6, plugging in a pi over 6 into the x's. But now we know we can write the same thing as r times e to the ix. R is 2. Your x is pi over 6, so it's 2 times e to the power of I times pi over 6. Boom. Done. Nice. All right. Here's your homework. Oh, look, cute. And yeah, that's it. That's it for chapter 13. We're going to have some review days and stuff like that, so you will be okay. You guys have a great day. Bye.